Hi everybody, welcome to another video in Calculus 2. This section is about trigonometric integrals. So pretty much we'll integrate integrals that have trig function, something like this. And pretty much we just have not just sine and cosine, individual function, we have more than one. And before we go there, let's just review some of the trig function we have. That's very basic, right? We will use the power reducing formulas. Sine square is equal to 1 minus cosine of double the angle divided by 2. Cosine is going to be a plus, and so we reduce the power by half and then double the angle to compensate that kind of. And this is from the double angle. We have sine of 2x is equal to 2 sine x cosine x, so divide by 2, we have that. And of course Pythagorean identity. So in this section there will be two types of integral. The first type of integral where we have power of sine and cosine. Another integral will have the power of secant and tangent. Cosecant and cotangent will be the same as secant and tangent. Right. So the first type, the integrals that have power of sine and cosine. So it will be in this form. Actually, it may be more in general. So we're going to have the power of sine, but the angle may not just x, it could be just kx. And then we have cosine to another power, and also kx. Now, if we have different values here, we still can do it, but a little more complicated. So now we just focus on the case where the multiple of the angle, the argument will be the same. Right, so focus on the integrals that have power of sine and cosine. Now there will be three scenarios. If the power of sine is odd, then we let u equal to cosine. And if the power of cosine is odd, we let u equal to sine. So pretty much whatever sine or cosine raised to an even power, we're gonna let the other one, whatever the power of sine and cosine is odd, we're gonna let the other be u. And if the power of sine and cosine are both even, then the power reducing, then we use the power reducing identities. That is those two. Yeah. So usually if this is the case, it is a little more complicated. Okay. Then of course there are one scenarios where we say, what if the power of sine and cosine, both of them are odd? Well, that is easy. If both of them are odd, we can use either one of these. So that's why we don't need to even write the case when both of them are odd. Right? Just use one of those. Right. Just jump right into the first example. Oh, it should be simple enough. Just gonna need to focus on this rule, and we'll just stick to that. Should not be any problem. Right. So first, when we look at this, obviously the power of cosine is odd. That means u is equal to sine. So as simple as that. Okay, so let's start with power of cosine is odd. That means let u equal to sine. Somewhere like that. And with that we can take derivative of u and then to find the x, we still do the same. So pretty much this rule go with the substitution, and that pretty much half of the section already. Right, so if that is the case, derivative is equal to cosine modulo dx over and then divide by cosine x. So we have du over cosine x equal to dx. Right, so we have the substitution with u and then dx. Now let this integral be I I'm going to substitute everything in. Sine square still there, cosine the cube, never mind. Yeah, by the way, the sine square we can just write like that, right? And the cosine, of course. Yeah. Now let's substitute here. Sine x is going to be u. I should have done this earlier. And then we have cosine cube. Either we write cosine cube like this or this, it doesn't really matter. I just want to. I should be able to comfortably interchange between the two. Right, du over cosine of x. That is the dx. Now we have u square cosine of x cancel with the cosine cube. We have a square left, so we have u square cosine square du. Right, so that's good. What's next? Next, we still have this x, so have to write this in terms of u before we can do anything else. So, and if we have an even power like this, square, even in particular square, then we can use the Pythagorean identity. So we have sine square plus cosine square is 1. Now if we want to solve for cosine square, we subtract the sine square on the other side. And we will substitute this into this. So the integral continue will be equal to u square 1 minus sine square and 1 minus sine square. Sine once again is u, so we have u square 1 minus sine once again is u square du, and this will be easy now. Multiply it out. U square minus u cubed u to the 4th du, and that integrate u square is u cubed over 3 and then u to the 4th u to the 5th over 5 plus c. And finally, we just substitute u as sine x. So I have sine cube over 3 minus sine to the 5th over 5. Let's see. So just like that. So this rule is very clear. Just stay exactly to that, and then there should not be any problem. And of course, this is just a substitution, regular substitution. Right, so that's what we have. Right, next we go to this example where we have sine square and cosine square. Now, power of sine and cosine, both of them are even. So when they are even, we have to use the power reducing identities. So that's what we're going to do next. So first, what we see is power of sine and cosine are even. If this is the case, use the power reducing. And the power reducing is sine square. I'm not going to run x, I'm use something else like a. Double the angle. And then if it is cosine, it's going to be a plus. Right, so we use the power reducing like that. So that integral from the beginning. So and rather than copy the problem, I'm just going to say the integral. Yeah. Right, that integral equal to sine square. I'm going to use this 1 minus cosine of 2x divided by 2, 1 plus cosine of 2x divided by 2. Right, let's multiply the top, multiply the bottom. Right, multiply the bottom. 2 times 2 is 4. Now the top, 1 times 1. 1 times cosine 2x. Minus cosine 2x times 1. And then minus cosine square. This cancels out nicely. And then so we just have 1 minus cosine 2x, cosine square of 2x on the top. Take the fourth outside. That's a constant. So we have 1 over 4 integral of 1 minus cosine square of 2x dx. Now, we still have a square, and if it's even, we can use the power reducing one more time. Now we use the power reducing of cosine square is 1 plus, the angle is going to be double, so here's 2x, it's going to be 4x. Now be careful where we split. It's going to be 1/2 and minus 1/2 and minus plus, so it will be negative 1/2 cosine of 4x. 1 minus 1/2 is 1/2. So 1/2 minus 1/2 cosine 4x. Now it's easy. We still have 1/4. Integral 1/2 is 1/2 x. And then we have 1/2. Integral cosine is sine, but we have to divide by the coefficient of x. So it's going to be multiplying 1/4. And then integral cosine is sine. And then we multiply it out. 1/4 times 1/2 is 1/8. 8. And 1/4 times 1/2, 1/8. Times 1/4, 1/32. Sine of 4x. So it's not that bad. So in this problem we use the power reducing twice. 3 times actually. 1 for sine, 1 for cosine, and then 1 for cosine square of 2x. So 3 times. Pretty much just those. Right. Next, on this one we have the power of sine is odd. By the way, there's sine square of 3x and cosine negative 2 of 3x. So in this case we still apply the same rule. Power of sine is even. Power of sine is odd, which means we're going to let u equal to cosine. Yep. But before that, so when we have the multiple of angle, just make a tiny substitution so we don't have to deal with the 3 there. So make that substitution. Let u equal to 3x. So when we substitute to u, we don't have to worry about the multiple of the angles. Derivative multiply the dx over divide by 3. And then we can substitute in the integral. So this integral is equal to sine cube of 3x. 3x is going to be u now. Cosine of to the negative 2 power. That is not the inverse square, but just cosine of negative 2 power u dx. Dx is du over 3. Now we'll take the 3 outside. And we have just sine cube of u cosine of negative 2 u du. Right. Then the same rule applies. The power of sine is odd. That means u is equal to cosine, the other function. So power of sine is odd, which means u equal to the other function. cosine of u. Let's not use u anymore. We must be something else. How about v? So let v equal to cosine of u. Right. Take derivative, and then we will substitute back into the integral. Right. So du dv over du. Derivative of cosine is negative sine multiply and then divide the negative sine u. Right, and this is equal to I. So now when we make the substitution here for that integral, you see what happened. We let u equal to sine, so that goes that sine is still there. Cosine of u to negative 2, so v is cosine, so this is v to the negative 2. Just use and then du, so sine cube v to negative 2, du is this. Right, sine cancel with one of the sine, so there will be a square left. The negative, take it outside of the integral. It will be sine square and then v to negative 2 dv. Yeah, the whole thing here cancel. Now this is just like the first example. We need to write everything in terms of v, so we have to take care of that, and the square from the Pythagorean theorem. That should be easy. I should say Pythagorean identity. Cosine square plus sine square is 1. This is u. If we want sine square, we're going to take 1 minus cosine square. And we substitute this into sine square. I'll continue on the integral. We will have negative on the outside first. That is 1 minus cosine square. And then v to the negative 2. Did we finish? Did we forgot something? Yep. There's the 1/3 here. Sorry. So negative 1/3. Don't forget that. Right. Sorry. And then we have v to negative 2 dv, except negative 1 over 3. Cosine, we did say cosine of u is equal to v. So here we have just 1 minus v squared to v to negative 2 dv. And let's multiply it out. Negative 1 over 3 v to the negative 2 and v squared and v to negative 2. Just 1. When we add the power, 2 minus 2 is 0. Anything to 0 power is 1. And then we just integrate. So negative 1 over 3, integral of v to negative 2 is v to negative 1 over negative 1. And then integral of 1 is just v. And then multiply it out. Negative 1/3 divided by negative 1. So negative and negative, that's 1/3. And negative 1/3 times minus 1 is going to be plus 1/3 v. And then v is cosine of u. I forgot the plus c. V is cosine of u. I'm going to write like that so we're not confused with the cosine inverse. And then 1/3 cosine of u. Right? This is not cosine inverse, so let's just write like that. And finally, u is equal to 3x. So we write that back in terms of x. Cosine of x to negative 1 plus 1 over 3 cosine of 3x plus c. By the way, cosine of 3x to negative 1 is 1 over cosine of 3x, which is turned into secant. So that actually turned out very nice. So 1 over 3 secant of 3x plus 1 over 3 cosine of 3x. I just run out of space. So but that is equal to secant. It's not cosine inverse. This is cosine to the negative 1 power. Right. So, like I said, the rules about what we let equal to u and what we let equal to sine or cosine, what do we let equal to u? That's very straightforward. Right. Now we have sine to the 4th dx. So it is even. When we have even, that is the power reducing. So let me write. So powers are even. Because the power sine, cosine are even, we're going to use when we have a square of a is 1 minus cosine of 2a divided by 2, and cosine is 1 minus, actually cosine is going to be plus double the angle divided by 2. Right. So first, when we have sine to the fourth power, we can write that as sine square and then square again. Right, but square a square here the sine power reducing. Sine square 1 minus cosine of double the angle divided by 2. So that is the power reducing, and then we square. And then when we square, we multiply by itself. Right. Let's hope we have enough space for this problem. And then multiply the top, multiply the bottom. This one does not simplify like the one we have before. The bottom is 4, that's easy. 1 times 1. 1 times 1 minus cosine of 2x. And minus cosine of 2x times 1. Cosine 2x and cosine 2x, that's actually a plus. Right, combine like terms. Right. What I'm going to do now is the fourth here, take it outside of the integral at constant. And we have 1 minus 2 cosine of 2x. And then plus cosine square of 2x. Now, we still have a square here, so that is the power reducing. One plus, it's going to be double the angle. And divide by 2, then dx. Right, so we have 1 minus 2 cosine of 2x. We're going to split plus 1/2 and plus 1/2 cosine of 4x dx. Right. 1 plus 1/2 is 3/2. then minus 2 cosine of 2x plus 1/2 cosine of 4x. Right. Now this is easy. This is easy. Now we can just integrate it. Integrate it. Three half x minus 2 integral of cosine is sine, but there's a 2x, so we have to divide by it, divide by 2, that is, and then integral of cosine is sine. Same thing, we have to divide by the coefficient of x. Integral of cosine is sine. So multiply it out, 3/8 and 2 and 1/2 cancel out, so that's just 1, so minus 1/4 sine of 2x, and that is 1/8, 1/4, so 1/32 sine of 4x. So that's what we have. So it's not that bad. Usually when we have an even power, we have to do the power reducing. Right. Next we have cosine to the 5th x and sine cube. So there's a lot of options here. Actually 2 options. Since the power of cosine is odd, we can let u equal to sine, and also power of sine is odd, so we can let u equal to cosine. Because both of them are odd, we can just choose u to be either cosine of x or sine x. So let me write that first. However, if that is the choice, usually it will be easier if we just take care of the higher power and we let u equal to that, so we don't have to worry about the power things. Right. So let me write this note. Right, so power of sine and cosine, both of them are even, I mean odd. So we can choose u equal to cosine of x or u equal to sine x. Now, even though we have those choices, it will be easier if we take care of the higher power, because when we have u, we don't have to worry about what's next. I'm going to write the other case as well, but for now, choose u to be cosine x. So the higher power, because of the 5th, so it will be simplified the problem if we take care of the higher power, even though we can choose either of those cases. Right, if u is the case cosine of x, then we take derivative. Cosine of x is sine, derivative of cosine is negative sine. Move the dx. And divide by the negative sine x. Right, let's do the substitution. Once again, let this integral be the integral I equal to cosine, that's going to be u to the fifth, and then sine cube still there. Dx is du divided by negative sine x. Sine x cancel out, and we take the negative power, move in front of the integral. So negative u to the fifth sine square du. And then we do the same thing, Pythagorean identity, substitute in sine square. So sine square equal to 1 minus cosine square. And we substitute into sine square here. Sine square is 1 minus cosine square. And cosine we let equal to u. Multiply it out, u to the fifth at u to the 7, and integral of that is u to the fifth to u to the 6 over 6 minus u to the 8 over 8 plus c. Distribute the minus. And u is cosine of x, so cosine of negative u cosine of x, so cosine of x to the 6 over 6 plus cosine of 8 to the 8 power of x over 8. Let's see. Right, so that's the first half of the section where we take care of the power of sine, cosine. The rule is very straightforward. Whatever is out, we let u equal to the other function. Unless, of course, when we have an even power all the way, then we have to use the power reducing that and that. Right. Next, we go to the integral that involving tangent and secant. For cosecant and cotangent, it will be the same thing, except it's going to be minus. Right, before we go there, just review real quick. Integral of tangent is that, and integral of cotangent is without the negative. And then integral of secant is that, and cosecant is that. We actually derive those formulas. So how do we prove integral of tangent? Well, that's easy. We did this already. Tangent is sine over cosine. Right. And as you see, both of them raised to the first power. By the way, I can do this. Move the cosine from the bottom to the top. If we write the negative 1 power. So I write like this, so we are not confusing with the cosine inverse. This is cosine of x to the negative 1. Because originally we have cosine of x to the first power by default. Move to the top, change to negative. Now, the power of sine is odd, the power of cosine is also odd, but just like the last problem, we will let something that to the more complicated power to be u. The other one is going to follow. So in this case, I'm going to let u equal to cosine of x, because that negative 1 power is more complicated. So power of let's say sine, cosine. But we choose the one with the more complicated. So we should go back to this instead of saying the higher. What I actually mean is more complicated. Let's use green. Yeah. So whatever more complicated, we're going to let that equal to u, so we don't have to worry about it. Because the negative 1 power more difficult to take care of. Right? So that integral equal to, wait, I haven't done the substitution properly. U equal to cosine du over dx is equal to negative sine. So if we want to solve for dx, it's going to be du over negative sine x. Right. Now, substitution. Sine x still there. Cosine is u to negative 1. And dx is du over negative sine x. And then take the negative outside. u to negative 1 power du. So the integral of negative and u to negative 1 is going to be ln of absolute value of u plus c, right? So negative ln of u is cosine of x. So that is one way to write the answer. Another way to do that is, if we take the negative, bring it inside, yeah. So take the negative 1 inside as a power. And negative 1 power, we can bring it down. Plus c. By the way, the absolute values here can extend to the whole quotient. And that gives us 1 over cosine is secant. So that's what we have. So it's not that bad. This is just another substitution, and we still use the same thing. Anyway, so good practice. Secant of x. Now secant of x is completely different things. We cannot do that like we normally do using the substitution. We can write secant is 1 over sine, and then we cannot let u equal to cosine. That is complicated things. What we can do though is this. I said this. Actually, this is kind of a classic problem. So any classic problem has a classic solution. What we do is we multiply secant x plus tangent x on the top. And you say, why do we do that? Well, when we get to the end, I will answer that question. Now multiply to the top, secant times secant, but with the bottom will stay. Secant times secant, secant square, secant tangent. Right. Now, it is a substitution. Let u equal to secant tangent. So we'll take derivative. Derivative of secant is secant tangent. And derivative of tangent is secant square. So the top is actually the derivative of the bottom, which is extremely nice. And that's why we multiply by it. And move the dx over, divide by that. So we have du over secant x tangent x plus secant square equal to dx. And now substitute into the integral. The top is still the same though. The bottom we let equal to u, and the dx we let equal to this. Conveniently they cancel out. Just have 1 over u du. And the integral of that is ln of u, ln of absolute value of u plus c. And u is that. Oh, sorry, that. Right. So if you ask the question, why did we multiply this from the beginning? So I suspect that in the past they have this and then they take derivative. It just happened to be secant. And then they reverse engineering since they have this. So look like we have to multiply by that. So kind of a genius way to do things. But here we know the answer already. It kind of reverse engineering. It's not that difficult. Right. That's a nice proof anyway. Alright, so of course also requires substitution, which is a lot. And the previous section we know that if substitution doesn't work, we can maybe iteration by parts will work, and we certainly will use that in a minute. But for now, the rules when we integrate with the power of tangent and the power of secant, and of course we can also have the multiple angles. Instead of x we have kx and kx here. But as it stands, that's complicated enough. Right. The rule here is a little more complicated than the power of sine, cosine. If the power of sine is odd, u equal to cosine. If the power of cosine is odd, u equal to sine. Both of them even, power reducing. Straightforward. This one is not. And it's straightforward too, but it's kind of a lot more difficult to remember. So the power of secant is even. U equal to tangent x. The power of tangent is odd. U equal to secant. Right? So a bit more difficult to use. And if the power of tangent is even and the power of secant is odd, so tangent is even and the power of secant is odd, use without identity. Didn't tell much, but usually when there's the case number 3 here, there will be a lot of work involved that. Right. So let's just look at the first problem. When we have secant square tangent dx. Now, let's check. If the power of secant is even, u equal to tangent x, so certainly the first choice certainly works. Now, also, if the power of tangent is odd, that's also the case. We let u equal to secant. So on this problem, both of them works. So I'm going to do both, obviously. That's what we draw a line here, right? So first, power of secant is even. So u equal to tangent x. And then here we can also use, say, the power of tangent is odd. u equal to secant right. So both of them works, and hopefully we get the same answer here. Actually, we should have the same answer here. Right, so if u equal to tangent, do the substitution. The derivative of tangent is secant square. And then if we want to solve for dx, move dx over, divide by secant square. Yeah, just multiply the dx and then divide by the secant square. I do that at one step. Now that integral equal to secant square, well, still there. Because we let u equal to tangent of x. So that is u. And dx is du over secant square. That cancels out and we just have u du pretty much. So integral of u is u squared over 2 plus c. And that is u is tangent, so tangent square over 2 plus c. Right. Simple enough. Now if we let u equal to secant, derivative of secant is secant tangent. Multiply dx and divide by it, so we will have du over secant tangent equal to dx. Multiply dx and divide by secant tangent. Now the integral will be equal to secant square, which is equal to u, so we have u square tangent x dx is that. Luckily secant x is also u, right? So I'm going to say du, and that's secant x here. That is u. That is u. And u square and u cancel out, so we still have 1 over u du, and integral of that is, sorry, It's not 1 over u, it's just u. Which is u squared over 2 plus c. So u is secant x, so we have secant square over 2 plus c. Right. Now, are they the same? They should be the same, right? Now, actually, they may not be the same. But in the form though, they should only different by a constant. That's what we should say. Right, now, in terms of Pythagorean identity, what do we have about secant square and tangent square? So the Pythagorean identity we're talking about is tangent square plus 1 is equal to secant square. Now the secant square here, we can rewrite that as tangent square plus 1. Right? So if we want to continue, secant square is tangent square plus 1. So when we split tangent square over 2 plus 1/2, each when the page number stand in the way, plus c. Right? We just split this and we have that. Now, the 1/2 is a constant, c is a constant, 1/2 plus a constant plus a constant, still a constant. So we don't do this a lot, but we can just combine this into one big constant. Sorry, now with space. So you have tangent square divided by 2, and this together is another constant. So just write c. When we write like that, those two are the same. Kind of, that constant may be different than this constant. So this constant definitely different than that constant. But so the answer is fine. By the way, in my math lab, when you enter the answer, you can enter this or that. They take both. Right. Now go to a classic problem of secant x cubed. Right, let's look at the rule first. What do we have for the rule? When power of secant is even, we don't have that here. When the power of tangent is odd, don't have that neither. If power of tangent is even and the power of secant is odd, use Pythagorean identity. Yeah, it looks like that what we have to do here. But oddly enough, as I mentioned before, this is another classic problem which we going to use which require a classic solution. Right. There may be another way to do it, but this is one way to do it. Secant, we can write secant x and then times secant square. And so why do we do that? Well, because it works, but I just want to say that. Because when we write secant and secant square, the secant square, the integral of this is easy, tangent. Secant, we can take derivative. So, remember, to get the idea, right? The idea is, this one can be differentiated, this one can be integrated. So what's that sound like? Integration by parts, right? one thing to be differentiated, the other thing to be integrated. So that sounds good, even though both of them are trig function. Right, so iteration by parts. Integration by parts. Right, let's use a table as we used before. This is not a traditional iteration by parts. We'll have two different kind of function. Both of them are trig here. So something to be differentiated, something to be integrated. And the second we're going to put in the differentiation. And then the secant square we're going to put in the integral. Because compared to the rule, integral of secant is rather complicated. But integral of secant square is just tangent. So the derivative of secant is secant tangent. Integral of secant square is tangent. Right, so let this integral be I. Now, I will be equal to iteration by parts. The first diagonal is positive. And then of course, since none of them vanish, we're going to stop. So we use the horizontal and we stop. The sides still alternate. But when we stop, we have to use the integral sign. So it'll be secant tangent tangent. Secant x tangent x times tangent x. Dx. So how did that help us? Not much. Secant tangent times tangent, so will be secant x tangent square right. Does that help us though? Well, it may. Look at the tangent square. Usually when we have the square, the Pythagorean identity will come in handy. So once again, tangent square plus 1 is secant square. Right. So tangent square is secant square minus 1. And that is tangent square. Tangent square is secant square minus 1. Multiply it out. Secant cube minus secant x. And then we split the integral. That is secant cube minus the negative, that's a plus secant x. So that's nice and all. And of course we see this trick before, right? If we say secant x cube is the integral, that also that. So what we have here is the integral I equal to secant x tangent x. Secant cube, that is also I. And the integral of secant is ln of secant. Sorry, ln of secant x plus tangent x. So we use that. Add the I on both sides, so we have 2I equal to secant x tangent x, and then plus ln of secant x plus tangent x plus c, and finally divide by 2. So the integral of secant cube is equal to 1/2 secant x tangent x. It's ln of secant x plus tangent x plus c. So it's not that bad, right? So the reason when we see the secant cube and we split equal secant and secant square, the only reason we do that, and then we use integration by parts, because the integral of secant square is tangent. So that works out nicely. And conveniently, when we have the tangent square, get us back to secant cube. And usually when we integrate and we do it in the cycle, in a circle, actually it is a good thing if we can move to the other side, then we can solve for that. And so we can do that indirectly. Once again, this is a classic problem, so because it has the classic solution, so will be that. Right. Next we have tangent square and secant x. Let's do the check again. Power of secant is even. Nope. Power of tangent is odd. Nope. So that doesn't help. What can we see here? So let's look at that. And so if the power like that doesn't work, so what we can do is, yeah, I did say it. What if we don't have that? What if we have the power of tangent is even? Yes. Power of secant is odd. Yep. Pythagorean identity. So use that. It might help though, right? So tangent square all the way up there is secant square minus 1. And then times secant. And then multiply it out. Secant and secant square. That's secant cube. Oh, we see this before. Minus secant dx. Right, that's good. Why don't we just split this in 2? And then the secant cube we just did. The secant we know the answer as well. So as is that. And we just did that, so we know the integral. It's 1/2. 1/2 secant x tangent x plus ln of secant x plus tangent x plus c. Sorry, still have the integral of secant, which is ln of secant x plus tangent x, then plus c. Right, because when we can multiply now to 1/2 secant x tangent x plus 1/2 ln secant x tangent x minus ln secant x plus tangent x plus c. And combine like terms, these two terms, 1/2 minus 1 is minus 1/2. So we have 1/2 secant tangent minus 1, so minus 1/2 ln secant plus tangent plus c. Right. It potentially be bad, but at least we did the secant cube before, so it's not all bad. Right. So the case where the power of tangent is even and the power of secant is odd, that usually requires a little bit of work. Other than that, we have some special scenarios to take care of that. Right, now secant to the 4th power. We did secant cube. Now we know secant. Okay. Integral of secant is this. Integral of secant square is tangent. Integral of secant cube is that. Now we do integral of secant x to the 4th power. So kind of get the idea there, right? Also, let's look at this scenario. Power of secant is even, so that's good. We have power of secant is even. So right away we have that. U equal to tangent. Good. Power of secant is even. So right away U equal to tangent of x. And you say, where's U? Where's tangent of x? And we don't have that. It's perfectly fine. Don't worry. We'll get there. Right. Let U be equal to tangent of x. We can check the derivative. Secant square. Yeah, at least with that. Move the dx over. And divide by the secant square. Multiply dx, divide by secant square. So there's dx, and there's u. So this is the integral I. Substitution, we still have secant x to the 4th, so just have to live with that. Dx is du over secant square. Right. Now secant to the 4th and cancel with secant square. There'll be secant square left. Right, then we say, oh, integral secant square tangent, right? Sadly, nope. The reason we cannot do that because this is x and this is u. So unless it is in terms of u, if it is secant square of u, then yes, this is tangent, but it is not. This is x, this is u. So we have to write everything in terms of u. And now let's go back to the rule we have earlier. We can have to write this as Pythagorean identity, right? Tangent square plus 1 is secant square. So why do we have to do that? Well, because u is equal to tangent. When we write like that, we have tangent. Right? So, secant square is tangent square plus 1. Still du. And tangent square is u square, which integral is u cubed over 3 plus 3 plus u, sorry. And then it's easy. Substitute it back, and so we will have u is tangent, so tangent cube of x divided by 3 plus tangent of x plus c. So it's not that bad. Yeah, even though the rules, at least the rule works when we have secant to an even power, u equal to tangent, even though we don't even have the tangent in the integral yet, but we'll see it soon enough. And yeah, that's where we see it, and then we can integrate. Right. The next problem, let's make it a bit more complicated and put the 2 in here. So tangent cube of 2x, or I should say tangent of 2x cube, which is the same thing. Or I just say it's tangent cube of 2x. Yeah, it doesn't matter. Let's check the rule though. Rule say power of secant is even. We don't even have secant. Power of tangent is odd. Yes, power of tangent is odd. So u equal to secant. Yep. Right, before we do that, let's do the quick change of the variable 2x here into something, just a single angle. So I'm going to let u equal to 2x if you want to. Or it doesn't matter. We just let u equal to tangent. Wait, what was that? If power of tangent is odd, let u equal to secant. Right, so I write that out. Power of tangent is odd. U equal to secant. Now we can say secant of 2x. Because the angle is 2x. So let u equal to secant of 2x. Derivative is going to be 2 secant tangent. So if we want to solve for dx, multiply dx and divide by that. So we have dx. And we have u. Right. Substitute it back. Integral tangent cube. I'm just going to say it. And there's no u, but there's the du. There's the dx, I mean. Substitute that. Two secant tangent. Cancel this. And then du over 2 secant of 2x. Right. Now what can we do here? Right, first, the secant 2x, that is u. Yes, so this is u. And the tangent square here, we have to use the Pythagorean identity. Because yeah, the two take the two outside. So we have 1/2 tangent square of 2x du, and that is u. So tangent square, just going to use a plus 1 is secant square. So tangent square by itself is secant square minus 1, and substitute into that. Secant square minus 1 du over u, and the secant square, and then I mean the secant is u, so we have 1/2 u square minus 1 du over u. Multiply it out. I mean, I can rewrite it as 1/2 u square minus 1 over u. So put the u at the bottom and put the du by itself on the back. U square divided by u. So we split that. So we equal to 1/2 u square over u is u, and then 1 over u du. Integral of u is u square over 2. And then ln of u plus c. And we have 1 over 4 u square minus 1 over 2 ln of u. And finally, u is secant of 2x. So we have 1 over 4 secant square of 2x minus 1/2 ln of secant of 2x plus c. So we see the multiple angle before. Either when we see the multiple angle, what was that? Yeah, here. So when we see the multiple angle, at first we can just take care of that multiple angle first, and we turn into this form. We continue doing that, or we just go ahead and just substitute directly and set whatever u equal to the multiple, the trig function of the multiple angle. It will take care by itself. That doesn't matter. But either way, just a substitution. There are a bunch of substitution here, but we do not call that substitution, trig substitution, because trig substitution is another thing that actually in the next section. So bottom line is, the most important things here is just the power of sine, cosine, and we're going to use this rule. If the power of sine is even, if the power of sine is odd, u is equal to cosine. If the power of cosine is odd, u equal to sine. And then and if we have tangent and tangent and secant, and likewise cosecant and cotangent, the rules is a little more complicated, but still apply that fully. I mean, we go straight forward to the rule. There's no exception here. Power of secant is even, tangent u equal to tangent. Power of tangent is odd, u equal to secant. And then the power of tangent is even, secant is odd. We use Pythagorean identity. The secant cube though is a classic case. So the solution, actually we use integration by parts, was split into secant and secant square, because integral of secant square is easy to do. Right, so we have the integral of tangent, certainly integral of tangent cube. So what happens if we have the integral of tangent square? I just want to write this quickly. What if we have the integral of tangent square? What the rule says. Power of tangent is even, or power of secant is odd. Use Pythagorean identity. So yes, we use Pythagorean identity, tangent square, secant square minus 1. Integral of secant square is tangent. Integral of 1 is x. Yeah, so we know integral of tangent, tangent square. This is tangent cube. And tangent square just tangent square plus 1 is secant square. So tangent square is secant square minus 1. Secant square integral is tangent 1 integral is x. And that goes. So pretty much it. So with that, I finish this section, because we cover everything I need to. As always, thank you for watching.